catch as many details as you can as we have our expert today. So without any further ado, we call him our rock star of road salt. He is a University of Iowa professor. He is a civil and environmental engineer, and he just pretty much knows everything there is to know about road salt, the chemistry of salt. So very simply, let's give him a warm welcome. Guys, want you to ask questions, so he will go over the protocol of like how you let him know if you would like to ask him questions. So,
Excellent.
all right.
All right, well, thank you all for having me. As we go through the class this morning, it's not impossible. There might be one or two terms I use, or concepts I raise, or ideas that come up that don't necessarily make sense. And rather than having you scratch your head or think, wow, I'll never remember that, we have a protocol that allows you to deal with it. So if you would, take your right hand and put it on the table in front of you. All right, right hand. Now raise that right hand. Okay. All right, so if an issue comes up, this is what you do. Raise that right hand, okay, and I will address that issue. I will have help from various folk here today to make sure that if you raise that right hand, I see it. Even if you're doing this, kind of shy. Okay. No need to be shy about it. This is what we do in college. Okay, so you now have one of the skills you will need for university. What we're going to talk about this morning is road salt, how it works, how best to use it. The map of the talk, we'll get into what road salt is, chemically. How does it work, chemically? Why do we use it? What are the benefits? What are the drawbacks of using it? How much do we use? What happens if we overuse it? And what can we do to make sure we don't overuse it? We get the benefits we want from using it while minimizing the negative drawbacks. So we're going to cover a lot. Road salt is mostly sodium chloride. Now, you've been looking at what Cedar Rapids uses on roads, right? 1, 2, not. This is what they use. It's sand, a little bit of sodium chloride, a little bit of calcium chloride. Take a look, pass it along, you've probably seen it. Road salt is mostly sodium chloride, but it's not by any means chemically pure. Here in the US, it's mined, and same in Canada. The mines in North America, Ontario, New York, Michigan, Ohio, Kansas, Louisiana, where most of the salt comes from. Because it's mined, it's fairly coarse, and it's a little bit dirty. It's about 95% sodium chloride. The balance is dirt and a few other chlorides. Magnesium chloride, calcium chloride, potassium chloride, depending which mine it comes from. It's fairly big chunks. Compare it to what you get out of the salt shaker at the dinner table. This is very, very coarse. Now, if you were to go to Europe, it would still be coarser than the salt you get out of the salt shaker. But it's a little bit finer because they get it in a different way. They take seawater and they evaporate the water off the seawater to leave what is known as solar salt behind. It's a somewhat finer gradation. It's still, as I say, coarser than table salt, but it's finer than what we use here. How does road salt work? Well, it's what we know as a freeze point depressant. What that means is if I create a solution of salt and water, it will have a freezing point lower than the freezing point of pure water. So what is the freezing point of pure water? Say again? 32 degrees what? Fahrenheit, yes. Can you speak Celsius or centigrade as well? Anyone know what it freezes at?
0 degrees.
0 degrees Celsius. So 32 Fahrenheit, 0 degrees Celsius. We need to be comfortable with both unit systems. Okay? When we add salt into the water, we create a solution. It's going to freeze at a lower temperature. And what that means is if you can get salt to go into solution with snow or ice, it will lower the freezing point of that snow or ice. Or some of that snow or ice will melt. And that's what we're looking for when we put road salt on the road. However, as we go through the chemistry, you will see that we do not melt very much snow and ice. We'll get into why that's not quite so bad a thing as you might think it is. But first, let's dive into the chemistry. How does this work? Well, we begin with what's known as a phase diagram. And this is simply a graphical representation of the salt-water system. In this case, salt is sodium chloride and water in solution. We have temperature down the vertical axis. We have the percent of sodium chloride by weight on the horizontal axis. And we notice that when we have no salt in there, when the percent of sodium chloride by weight is 0, our freezing point is 32 degrees Fahrenheit. Yes, we have a data point we can recognize. This is always helpful. As we add more salt into our solution, the freezing point drops until finally we get down to the bottom of the V here when it begins to rise on the other side. Okay, the bottom of the V here is known as the eutectic point. That's E-U-T-E-C-T-I-C, eutectic. It's a really good word to bring up at the dinner table. When your parents ask you, as they always do, what did you learn in school today? You could say, eutectic, and pray that that shuts them up so they don't ask any other questions. Okay. As long as we are in this area here, called brine, we're not going to have any ice. But if I'm a solution in here, and something happens to cause me to dilute, I know, I melt a little more snow and ice. Then I'm going to move this way on the diagram and eventually cross this line. If I'm in that brine area here and the temperature starts to drop, I will move down on the diagram and eventually cross that line. And the significance of that line is once I cross it, I'm no longer just a liquid. I'm a liquid with ice in it. I become slushy. I become slick. If you like, that line is a here be dragons line. If I cross that line, bad things might begin to happen. So, we want to stay here. We've got a reasonable description of our salt-water system. It's a solution rather than just a mixture or a suspension. What's the difference between a solution and a suspension? Okay, yes? That's part of it, yes. If I have a suspension, can I separate it into its constituents by filtering it? Yes. If I have a solution, can I do that? No. A solution will not separate into its components if I filter it. They're stuck together. Okay? And that's kind of important for us because this is not going to come out of solution unless we cross that here be dragons line. But actually what's going to happen is some of the water is going to come out of solution and turn into ice. And there be dragons. Okay. So let's use that information in that phase diagram to figure out how much snow and ice we can melt if we put a certain amount of salt down on the road. So we'll do an example. We're going to put 300 pounds a lane mile of salt on the road. What's a lane mile? What's a lane mile? No one? Yeah? Yeah.
Like
One side of the road is one lane, right?
Yeah.
So a lane mile is one lane for 1 mile.
Yeah.
It's a measure of area. A lane is 12 feet wide. And if it's 1 mile long, we've got 1 mile, which is going to be 5,280 feet multiplied by 12 feet. It gives us an area in terms of square feet. So it's a measure of area. We put down 300 pounds for this particular unit of area. We're going to do that at a pavement temperature, 23 degrees Fahrenheit, which is a very convenient temperature because it also happens to be a whole number in centigrade as well. It's -5 centigrade. That's a pavement temperature, not an air temperature. The two are different. You can go on to a Department of Transportation website, see on a page called Weather View all the pavement temperature sensors around Iowa. And they'll show you at many of those locations both the pavement temperature and the air temperature. And the two are different. And from the point of view of the chemistry, we do not care about the air temperature because the salt is on the pavement when it's doing its work. So it's the pavement temperature that matters. We're going to ask the question, how much ice can we melt? And to figure that out, we have to ask a sub-question, if you will. Okay, at what point, at what percentage at this temperature would we cross the here be dragons line on the phase diagram? Here's our phase diagram again. It's looking a little different this time. Okay, we've got one curve here for NaCl, which is sodium chloride, and another curve here for, what's CaCl2? Calcium chloride, yes. Why is it Cl2? Yeah? Yeah, but that's not why we have Cl2 there, yeah? NaCl, sodium chloride, is one sodium atom, one chlorine atom. CaCl2 is one calcium atom, two chlorine atoms. Okay, that's where the two comes from. All right, you'll notice CaCl2, calcium chloride, goes down to a much lower temperature. You'll also notice up around -5 Celsius, there really isn't a whole lot of difference between the two. In fact, both of them cross that here be dragons line at approximately 7.5 to 8%. Let's call it 7.5%. So, if we take our 300 pounds of salt, a lane mile, and we add a quantity of water to it, such that we now have a solution that is 7.5% sodium chloride by weight, then that will just be on the line where it's going to start freezing. That will then give us a quantity of water that we spread out over that lane mile, and then we'll figure out how deep that is. How much water do we need to add? We need to add 3,700 pounds of water. Because if we do that, we now have 4,000 pounds of solution, and 300 pounds of that 4,000 pounds is salt, which turns out to be 7.5%. So we've got to take 3,700 pounds of water, which is nearly 2 tons of water, and spread it out over a lane mile and see how big it is. And if we do that, here's our, get me out, Here's our 3,700 pounds, the lane mark. Here's our lane mark. It's 5,280 feet long, it's 12 feet wide. We've got a nice little magic number here of 62.4 pounds per cubic foot. Anyone know what that is? Never let your instructors get away with magic numbers. Okay, we do it all the time. We sneak numbers in on you. What is that? That is the density of water in pounds per cubic feet. Crunch those numbers, and you come up with a depth of water of 0.011 inches, 11 thousandths of an inch of water. Really, that's all that we can melt with 300 pounds of salt. Well, it's not quite as bad as that. I mean, snow is a little less dense than water. It's about a 10-to-1 ratio. So that's, okay, it's not 1/100th of an inch, it's about 1/10th of an inch of snow. And if you listen to the radio on the TV, or not the radio, the weather on the TV or the radio or the internet, if they are predicting 1/10th of an inch of snow, they will call it at best a dusting or maybe flakes. It's nothing. And that is close to the technical term we use to describe this. That is diddly squat. But wait, we know it works. That's actually quite a high application for that temperature, 300 pounds of lane mark. And yet, we only melt 1/10th of an inch of snow. Yeah. It's because we don't use road salt to melt snow and ice. I mean, you can, but it's incredibly wasteful. We use road salt to stop the snow and ice sticking to the pavement. In the best case, we put it down as a layer that prevents the snow and ice ever freezing to the pavement. The reason for that being, if we never freeze to the pavement, we never have to melt that bond, which puts us on a good side of an energy balance. But even if we do freeze, we still have to melt that bond. That's all we're interested in melting. A teensy tiny bit of snow and ice. Because we get rid of the snow and ice with the snow plows on the front of the truck. We push it off the side of the road. Melting it is not a good thing to do. We melt enough, and only enough, to prevent it. Okay. But why do it at all? It comes down to a couple of reasons we can sum up as safety and mobility. As of right now, each year about 7,000 people in the US die in winter weather-related crashes on the roads. It's an awful lot of people. If we're using road salt properly, and that's a word that we'll talk about, what properly means, then we can reduce the number of crashes by about 85%. That's a lot fewer people being killed. It's not just the safety side of things, though. Keeping the roads open and functioning is very, very important for our economy. I-90 is one of the major east-west interstates in the US. It ends up in Seattle, Washington, on the west end. And shortly before it gets to Seattle, it goes over a mountain pass called Snoqualmie. It's not terribly high, about 4,000 feet, but it gets a lot of snow. And every hour that road is closed down costs about $700,000 in lost economic activity. If Iowa gets shut down for a day by a bad winter storm, it costs about $60 million in lost economic activity. And the numbers keep on like that. Boston has been hammered by snow over the last 3 weeks. They've not had their transit system operating for the last week. They will have lost in economic activity hundreds of millions of dollars. A single storm in New York City a couple of weekends ago, the estimate is $200 million of lost economic activity in New York City alone. It's a huge impact, and it's something we have to consider as part of a sustainable approach to winter maintenance. Okay, sustainability, is that a word you have heard? Has that come up in various contexts? I see a few nods. Could be people about to fall asleep, but you never know. Okay. It involves balancing a number of things. It involves balancing societal needs, things like safety and the economy. Balancing them with costs and with environmental concerns. This is part of what it means to be sustainable in our road system. We have to provide safety and mobility. Now, safety and mobility comes at a cost. It comes at an economic cost. It's a number of dollars to run the plows, put the material down. And it comes at an environmental cost, a certain quantity of material in the environment. How much road salt do we use? Well, I can guarantee they've used a lot more road salt in Boston over the last 3 weeks than we've used here in Ireland over the last 3 weeks, because it depends on the winter. Last winter was particularly bad in the Midwest. We got a lot of snowstorms, not terribly big ones, but one after another after another. Used a lot of salt. This winter, not so much. Pretty cold at the moment, salt wouldn't work. But that's not the only thing that impacts how much we should use. It's how you use it. One of the things Iowa DOT does, and they're a leader in the world, in fact, in this regard, is they use salt brine. They take some of their rock salt and they mix it with water to get a 23.3% solution. Why 23.3? Think back to that phase diagram. That's the percentage for that eutectic concentration, right? Where you're going to get the lowest temperature that it will freeze at, the bottom of the bead. They then put out that brine before it begins to snow. And they do that every time. Why? They are in essence coating the road with a protective coating so the snow never gets a chance to freeze to the road. And they use a lot of brine. They use somewhere in the region of 15 to 20 million gallons of brine. Compare that with Minnesota, who use 2 to 3 million gallons of brine. Wait a minute, isn't that wasteful of Iowa? Well, it depends how you run the numbers. Suppose we take the max here, 20 million gallons of brine. Each gallon of brine has about 3 pounds of salt. So 20 million gallons is 60 million pounds of salt. Sounds like a lot of salt, and it is. But if you express it in tons, and there's 2,000 pounds per ton, well, that's 30,000 tons of salt, which still sounds like a lot of salt, and it is. And in addition to that, Iowa uses somewhere between 100 and 200,000 tons of road salt in solid form on the roads each year. So somewhere in the region of 200,000 tons of salt. Minnesota uses 2 to 3 million tons or gallons of brine, but they use about 800,000 tons of salt. So Iowa, by using nearly 10 times as much brine, uses about a quarter of the total salt that Minnesota uses. It's a pretty good deal. personally, and I'm not biased in this at all, the roads in Iowa are much better in the wintertime than the roads in Minnesota. And you should never believe anything a professor tells you. You should always check it out for yourself. Anyway, if we look nationwide, there's a pretty clear historical trend here. Back in the 40s, hardly anyone used salt. Came up to a peak sometime in the 80s of around 10 million tons a year. And since then, since the early 90s, it's been bouncing between 10 and 20 million tons a year. That's a lot of salt. But if we use it right, we get the benefits from it. All right. But what do we mean by using it right? Well, the first thing we have to be aware of is that all the salt that we put on the road, every bit of it is now in the environment. If we use 20 million tons of salt in a winter, that is all in the environment. It does not magically disappear and go somewhere else. So if we use more salt than we actually need to achieve the road condition that we want, then what we're doing is we're putting a loading on the environment, more salt, and not seeing any benefit for that loading, right? It's an excessive use of salt, and it's nothing but a negative for us. If we use the right amount of salt, then we will get all the benefits that we can set against the drawbacks. Now, what are the drawbacks? Well, the salt is going to go into either surface water, those are lakes, rivers, streams, or groundwater. Those are things that go underground and feed wells and so on. That's a negative from using salt. But any other option we use also has negatives. We could use sand. But sand gets ground up on the road surface, gets into very fine particles, about 10 microns in size, and can cause respiratory problems. That's somewhat negative as well. In fact, there are cities in the US, like Portland, Oregon, do not allow sand to be used at all because they have air quality problems. There are other cities, Denver, Colorado, they can use sand, but if they use it, they have to vacuum it all up within 72 hours after the end of the storm. Once they vacuumed it up, they can't reuse it because it's now classified as a hazardous material. So it has to go into a dump, basically, into the landfill. All right, sand has negative consequences. What about other chlorides? We could use calcium chloride or magnesium chloride. Yes, we could. But the problem with sodium chloride is primarily the chlorides. And calcium chloride and magnesium chloride have chlorides as well. So going to those doesn't get rid of the chloride issue. We still got it. We would need approximately the same quantity of the materials, so we'd still have a problem. Surely there are other chemicals. Yes, there are. If you look at what the airports use, they're not allowed by the Federal Aviation Administration to use chlorides in airports because chlorides corrode planes. And planes that drop off wings because of corrosion are not good things to be on. Okay? So they use what are known as acetates. There are two in particular, calcium magnesium acetate and potassium acetate that they use. A couple of negatives associated with those. But first, let's look at the positive. No chlorides. Free. Substantially more expensive than salt. Not good, but you know, under the right circumstance, that might be a trade we'd be willing to make. The real issue, though, comes with an environmental consequence in relation to surface waters. Acetates in rivers and streams and lakes degrade. They are an organic chemical, and they break down, and to break down, they need oxygen. So they take oxygen out of the rivers and the lakes and the streams. they have what is known as a very high BOD, or biological oxygen demand. So yes, they work. But no, they are not without environmental consequences. The shorthand way I think of this is every solution has a problem. Every solution that we might consider to get our roads safe in the wintertime has a problem. Even, yes, doing nothing. Leave aside the fact that if we don't treat the roads, we're going to have more people dying, and we're going to have less economic activity. We're still going to have negative environmental consequences. Because every car crash is a mini environmental disaster. Spilling in one very concentrated location, gasoline, diesel, engine lubricants, coolants. And there's the energy cost of replacing the vehicles that are destroyed. Anything we choose to do is going to have an environmental consequence. So, just as we balance the safety and mobility, the societal concerns, with the economic concerns, what's it going to cost us to do this, we also have to look at the environmental impacts. Anything we do has an environmental impact. They're different, but they're there. So, what happens if we overuse salt? We end up like Illinois. Not like all of Illinois, but if you can see here, there are a number of light blue areas on the map. Those are areas in Illinois where TMDLs have been established for chlorides. TMDLs are total maximum daily loads. What that means is government agencies are looking at the surface water in those locations to measure the chlorides on an ongoing basis. And if those chlorides get above certain levels, then you can't use salt or mag chloride or calcium chloride on the road until they drop back down below that level. What's up here where all the blue is? Come on, Illinois. What's here? Well, there's a Great Lake here. What's on shore? Chicago. They use way too much salt in Chicago. They do a bunch of bad things in Chicago. So, yeah, you can overuse the salt. And if you do, bad things can happen. How do we deal with this? You need to get the right amount of salt in the right place that's on the pavement surface between the pavement and the snow at the right time, so you don't allow the bond to ever form. And you keep it there, and you only add more salt as you need to. We've talked about how using brine, like Iowa does, can minimize the total amount of salt you use. Now that requires certain special equipment. Not every agency has it, but something agencies can do more cheaply than that is to pre-wet the material. The salt, when it leaves the truck, falls onto a spinner and gets spread on the road. You can mix in brine with that at about 8 gallons of brine per ton of material. And that pre-wets it, so you get certain benefits. If I put down my material dry, I will lose 30% of it into the ditch right away. If I put it down pre-wet, that's the dark columns here, I'll only lose 4%. This leads us to what we might consider a no-brainer type of situation. If I'm putting it down dry, let's suppose I'm putting down 400 pounds a lane mile. 30% of that, or 120 pounds, goes straight into the ditch. Leaves me with 280 pounds on the road. Okay, that 120 pounds in the ditch has given me no benefit at all. It's pre-wet instead. And instead of putting down 400 pounds a lane mile, let's only put down 300 pounds a lane mile. Well, I'm going to lose 4% of it. 4% of 300 pounds is 12 pounds. So 12 pounds is going to go in the ditch. It's not going to do us any good in the ditch. But 12 pounds in the ditch is better than 120 pounds in the ditch. What's real interesting is I still have 288 pounds of my 300 pounds on the road. So if I pre-weigh, I can use 100 pounds a lane mile less, 25% less, and actually get more salt on the road than if I put it down dry. That's a no-brainer. Now, turns out you can take it a little further. You can, instead of adding 8 gallons a ton, maybe add 50 or 70 or even 100 gallons a ton and create a slurry. You mix it up in a bit of equipment at the back of the truck like this, and it falls on the road and looks like this. Why brown? Well, I know you've done a certain amount of work with beet juice, right? You may have come across beet juice. Good, somebody's nodding, yes, okay. All right, beet juice. If you mix that with the brine, and you don't need very much, only 10% of the brine needs to be beet juice, you'll make it kind of sticky. It also gives it this brown color. That means it persists for longer on the pavement. It stays around longer than if you just use salt. Okay, that's a good thing because again, it's keeping the salt where we want it. It does us good on the pavement. It does us no good in the ditch. So keeping it on the pavement is good. And this is what it looks like when it's pre-wet at a rate of about 70 gallons a ton. It's a little disturbing to follow a truck like this because it doesn't bounce out of the back, it plops out the back, and the whole truck looks a little bit like a fecally incontinent cow going down the road. How much should we apply? Well, the bad news here is it's very, very variable between agencies. We are moving in the right directions here, but we're not quite there. In the ideal, you should vary the amount you put down depending on the type of storm and the pavement temperature. And also another thing called route cycle time, but many agencies, they only have one sort of cycle time, so they don't need to worry about that. Here's an example from Illinois, and this is to make up for hitting on them earlier and telling them that they were useless. They do have a good application rate time. Notice a couple of things here. If the pavement temperature is above 32, don't use salt. Why not? You don't need to. When snow hits the pavement and the pavement is above 32, what's going to happen to the snow? It'll melt. Now, eventually, yes, the pavement will cool down, so you can take heat out of it. But if you apply nothing and just monitor, you'll go. They say below 5 degrees, don't use salt at all. I might quibble with them a little and say, 5 is a bit low, maybe that should be 10. But they're absolutely right. At 5 degrees pavement temperature, salt is not going to be effective in the field. In my lab, it will still melt ice. But in the field, it just takes too long to be effective. In between, well, I vary what I put down according to my storm type. And as I get colder, I use more material. And that's the way it should be. More and more agencies across the U.S. are using charts like this to guide them with what they put down on the road. Two key things here. When we're above freezing, we don't need chemicals. We might put down a brine treatment because we know we will eventually end up below freezing. But we don't go out and just put chemicals on the road because it makes us feel good. When we're below around 10 degrees Fahrenheit, I would say, salt really isn't going to help us. We've got to really have a good reason to use it. One good reason might be if we've had a cold stretch, the temperature is warming up and we're going to have a bright sunny day, then we might put some salt down in the hope that it would break up some ice on the road, but it's not normal to do that. And then using liquids as our pre-treatment can be a huge help. So to wrap things up, road salt is a tool. It's a tool that used properly can be extremely effective. But like any tool, it can be misused. A hammer is a tool. It's really very, very good at some things, but as an example, it's not terribly good for changing light bulbs. Okay? Road salt is like that. There are things that we can do to make road salt work well for us. And we need, around the country, to be using those things. We may have a minute for questions. So, any questions? They are stunned into silence.
I'll just wait for the first person to go.
Yeah.
All right, and again, guys, before you leave, the University of Iowa has some things that you can take as you go. Those